In today's lecture, we're going to talk about the cross product. But before we get into that, let's review a little bit of what we've learned about lines and planes from our last two lectures. In our first example, we're looking for the point of intersection between the plane 4x minus 3y plus z equal to 31 and the line r of t. The challenge here is that our plane is given to us in terms of x, y, and z, and our line is the parametric vector equation of a line. It's given to us in terms of t. So we need to use the parametric equation of a line to rewrite r of t in terms of x, y, and z. In parametric form, x is equal to the first component of our vector, giving us x is equal to 2 plus t. Y is the second component, 3 minus 2t. And the third component, z, is equal to 6 plus 3t. Using that, we can sub in place of x in our equation of the plane, 2 plus t. We can sub in y equal to 3 minus 2t, and z equal to 6 plus 3t. Subbing in, we have 4 times 2 plus t minus 3 times 3 minus 2t plus z, and in place of z we have 6 plus 3t, and that is equal to 31. Simplifying on the left-hand side, we have 8 plus 4t minus 9 plus 6t plus 6 plus 3t equal to 31. 4t plus 6t is 10t plus 3t gives us 13t on the left-hand side of our equation, and this is equal to 31 plus 9 gives us 40, minus 8 minus 6 leaves us with 26 on the right side of our equation. Solving for t, we have that t is equal to 2. Subbing that back into our equation of a line, r of 2 is equal to 4, negative 1, 12. That's a vector, and we're looking for a point of intersection. So make sure that you always write your final answer as a point and not a vector. Here, our point of intersection is 4, negative 1, 12. The next example, same idea here. To find the point of intersection, we can sub 1 plus 2t in for x, 1 plus 3t in for y, and 1 plus t into z, all into the equation of our plane, and then solve for t. Doing so, we get 4 times 1 plus 2t minus 3 times 1 plus 3t plus, in place of z, we're subbing in 1 plus t, equal to 31. Simplifying on the left-hand side, we have 4 plus 8t minus 3 minus 9t plus 1 plus t equal to 31. Leaving our variables on the left-hand side of the equation, t plus 8t is 9t, minus 9t leaves us with 0 on the left-hand side of our equation, and getting all of our constants onto the right-hand side of the equation. 4 minus 3 is 1, plus 1 is 2, subtracting 2 from both sides, we get 29. Since 0 is clearly not equal to 29, that tells us that there is no point of intersection. And so, r of t must be parallel to the plane. Is there an easier way that we could have done example 2? How can we quickly check if a line and a plane are parallel? A line has a direction vector, d, and the plane has its normal vector, which we call n, and they are parallel if and only if the vector d is orthogonal to the normal vector. And that's true if and only if the dot product between the direction vector and the normal vector is equal to 0. A quick sketch helps to confirm this. I'll label our line r of t, and the plane has a normal vector, n. If the line is going to be parallel to the plane, then that line must be perpendicular to the normal vector. If ever you're in doubt, a quick sketch really helps to make it clear whether they're parallel or perpendicular. Let's go back to example 2 and let's check our work. The normal vector from our plane is equal to 4, -3, 1. The direction vector of our line is 2, 3, 1. Taking the dot product between the normal vector and the direction vector, we get that this is equal to 4 times 2 plus -3 times 3 plus 1 times 1, giving us 8 minus 9 plus 1, which is 0. Since we can so easily check, we can do the dot product in our head. For these types of questions, that's a good place to start, is just quickly look at the normal vector of the plane, the coefficient of your x, y, and z term, and the direction vector of your line, which is the coefficient of the t terms. Take the dot product. If you get 0, then prove that the lines are parallel. If you do not get 0, then keep going like we did in these two examples to find the point of intersection. Given two planes in R3, they're either not parallel, which means that there's a line of intersection. They are parallel, but they're distinct. Or the third option is that the two planes are parallel and the same plane. In example 3, let's determine if our two planes are parallel. And if they're not parallel, we'll find the line of intersection. We know that parallel planes have parallel normal vectors. Checking to see if these two planes have parallel normal vectors, the normal vector of our first plane is 1, 3, 1. And the normal vector of the second plane is 1, 1, 5. Telling us that one normal vector is not a multiple of the other normal vector, where c is equal to a scalar. And so that tells us that the planes are not parallel. To find the line of intersection, we could solve for one variable in one of the planes and substitute it into the other plane, and then solve for the remaining variables. Or I like to eliminate a variable by subtracting one of the equations from the other, or sometimes you'll have to subtract a multiple of one of the equations from the other in order to get one of your variables to cancel out. Equation 1 is x plus 3y plus c equal to 7. And from that, we want to subtract x plus y plus 5z equal to 13. Our x's cancel out. 3y minus y is 2y. Z minus 5z is a negative 4z, equal to 7 minus 13, which is negative 6. We can either solve for y or z, it doesn't matter which. In this case, I think it's a little easier if we solve for y. Let's divide everything through by 2 and then add our z term to the other side, giving us y is equal to 2z minus 3. Let's sub this equation into our first equation of the plane in place of y, giving us x plus 3 times 2z minus 3 plus z equal to 7. Distributing the 3 and solving for x, we have that x is equal to 16 minus 7z. We now have both y and x in terms of z. we know that our equation of a line is going to be in terms of t. So to parameterize these equations, let's let z equal to t. Subbing z equal to t into x, we have that x is equal to 16 minus 7t. Subbing z equal to t into y gives us y equal to 2t minus 3. Z is equal to t. This is the parametric equation of a line. Or we could write it in the parametric vector form, giving us r of t equal to 16, negative 3, 0, plus negative 7, 2, 1 times t. This is the parametric vector equation of a line. On the last slide of lecture, I worked out an alternate method of solving for example 3. It uses the cross product, which we haven't quite gotten to, but it's interesting to see two different methods for finding the line of intersection between two planes. In example 4, we want to find the normal equation of the plane containing the points A, B, and C. We know from our last lecture how to find the normal equation of a plane given a point and a normal vector. We also know how to find two vectors lying in the plane when we're given 3 points. But how do we go from two vectors lying in the plane to finding a normal vector to the plane? To do this, we have to use the cross product, which is what today's lecture is all about. V cross W, notated by a x in between the two vectors, takes two vectors as inputs, just like the dot product does, but unlike the dot product, which returns a scalar, the cross product gives us back a vector. The cross product also only works when we're in R3. Well, that's not completely true. The cross product will also work in R7. Let's look at the cross product both geometrically and algebraically. V cross W is perpendicular to both V and W, and the three vectors V, W, and V cross W follow the right-hand rule. Imagine vectors V and W lying in the plane of your paper. Lie your hand perpendicular to the plane with the edge of your hand lying along V and curl your fingers towards W. Your thumb should be pointing straight up, telling us that V cross W is coming out of the page. If we switch the two vectors, in order for your hand to lie along V and curl towards W, your hand has to be upside down or lying underneath your paper. When your fingers curl towards W, then your thumb is pointing down, telling us that now V cross W is going into the page. Vectors have two components, direction and magnitude. Using the right-hand rule, we know the direction of our vector. The length of V cross W, or the magnitude, is equal to the magnitude of V times the magnitude of W times sine theta. A little word of caution, though, do not find angles this way. Yes, it works, but we have a formula with the dot product. We know that U dot V is equal to the magnitude of U times the magnitude of V times cosine theta, and dot products are way easier to find than cross products. So you should never spend the time finding an angle using the cross product. Speaking of finding the cross product, algebraically, V cross W is equal to the vector. In the x component, we have V2 times W3 minus V3 times W2. In the y component, we have a negative V1 times W3 minus V3 times W1. In the z component, we have V1 times W2 minus V2 times W1. That is a lot to memorize, but luckily, we have a better way than just brute force memorization of this formula. Let's take a look. Most of you have done a little bit of linear algebra when you were in high school. Recall that in R2, we can find the determinant of a matrix by taking the product of the down diagonals, which gives us V1 times W2, minus the product of the up diagonals, giving us W1 times V2. A quick word on notation. Square brackets mean that we're talking about the matrix itself. The straight bars means you're taking the determinant of the matrix. It's an operation you're performing on the matrix. Just like when you're dealing with vectors, you have V cross W or V dot W. In scalars, we talk about addition and subtraction. Same thing for matrices. Whenever you see those straight bars, that means that you should take the determinant of that matrix. In R3, we have two different ways that we can find the determinant. The first way uses the same idea as in R2, but we scale it up to R3. Since we're looking for the determinant, I'll put our matrix inside the straight bars. To find the I component, you cross out the row that I is in, and you cross out the column that I is in. And then you're left with a smaller 2 by 2 matrix, which we know how to take the determinant of. Multiplying that by I, we have V2 times W3, the product of our down diagonals, minus W2 times V3, the product of our up diagonals. Just like above, where we had the first component minus the second component, we need a negative sign, giving us minus j, crossing out the row that j is in and the column that j is in. We now find the determinant of the 2 by 2 matrix, V1 times W3, minus W1 times V3. The signs alternate, so we're back to a plus k, crossing out the row that contains k and the column. The determinant of the remaining 2 by 2 matrix is V1 times W2 minus W1 times V2. The nice thing about this method is that it works in any dimension. So as you continue on in linear algebra or computer science, and you want to take the determinant of larger matrices, this method still works for you. And the signs of your unit vectors always alternate between positive and negative. Since we're only in R3, that means that I and k will always be positive, and j will always be negative. The second method is what I call the basket weave method. To do this, you have to repeat the first two columns of your matrix. Copying over our I column and our j column, we can now take the sum of the products of the down diagonals minus the sum of the products of the up diagonals. Let's highlight the down diagonals in orange. Our first down diagonal is equal to I times V2 times W3 plus the product of our second down diagonal, J, times V3 times W1 plus the product of our third down diagonal, K, times V1 times W2. From that, we subtract the sum of the products of the up diagonals. We'll do the up diagonals in yellow. Our first up diagonal is W1 times V2 times K, plus the next up diagonal gives us W2 times V3 times I, plus the product of our third up diagonal, W3 times V1 times J. From here, we have to group our like terms. We need to get all of our i's together, all of our j's together, and then all of our k's together. Looking at our I terms, we have V2 W3 minus W2 V3 times I. Looking at our terms with a J, we have minus W3 V1 minus V3 W1 times J. And I pulled the negative out of here because the sign of J is always negative. So it just makes it more consistent with the formula that we used above and that I gave you on the previous page. Grouping together our K terms, we have plus V1 W2 minus W1 V2 times K. Our answer using the second method, the basket weave method, lines up with the earlier method. However, unlike the first method, the basket weave method only works in R3. While it's a very nice method for us of finding the determinant, since we'll never scale above R3, the first method is applicable beyond just this semester. But it's really up to you guys. Whichever method you prefer is totally okay. Now that we have the formula for the cross product, let's try an example. In example 5, we have two vectors, u equal to 1, 0, 3, and v equal to 3, negative 2, negative 1. In part A, we want to find u cross v, and we'll use the first method to do so. We'll begin by writing our matrix in 3 by 3 form. The top row will always be I, J, K. The second row will always be whichever vector comes first in the order of the cross product. So we want to copy down u equal to 1, 0, 3. The bottom line of our matrix will be the remaining vector, 3, negative 2, negative 1. This is equal to crossing out the row that contains I and the column that contains I and finding the determinant of the remaining 2 by 2 matrix. We have 0 times negative 1 minus negative 2 times 3 times I minus, looking at our J component, the product of our down diagonals is 1 times negative 1 minus the product of our up diagonals, 3 times 3, times our J component, plus, looking at our K component, we have 1 times negative 2 minus 3 times 0 times K. This is equal to 0 minus a negative 6 gives us 6i. Negative 1 minus 9 is negative 10. Negative 10 gives us plus 10j. In our k component, we have negative 2 minus 0 times k, giving us negative 2k. It's fine to leave your answer just like this, or if you want to put it in vector form, you can write it as 6, 10, negative 2. Either form is okay. In part B, we're using the same two vectors, but we've switched the order. Now we want v cross u. Let's use the second method, just so that you can have an example using each method. I'll start by writing out our matrix like we did before. In the top row, we have I, J, K. In the second row, we now have whichever vector comes first in the order of your cross product. So we want to write our vector v, 3, -2, -1. In the third row, we have the second vector, 1, 0, 3. Using the basket weave method, we want to copy our first two rows down again. We want the sum of the product of the down diagonals, which is -2 times 3 times I, plus -1 times 1 times j, plus 3 times 0 times k. This is the sum of the product of our down diagonals, and from that we want to subtract the sum of the product of our up diagonals. Our first up diagonal, we have 1 times -2 times k, plus 0 times -1 times I, plus 3 times 3, I'm a little short on room, so I'm just going to write that as 9j. Simplifying and grouping together our terms with an I, we have -6 minus 0, which is equal to a -6 times I. For our j terms, we have -1j minus 9j, giving us -10j. For our k terms, we have 0k minus a -2k, giving us plus 2k. Just like above, totally fine to leave your answer in this form, or if you prefer, you can write it in vector form as -6, -10, 2. Comparing our answer, you can see that this is the negative of our answer from part A. Can we generalize? Is this something that will always be true? Let's look at our unit vectors. I extends 1 unit in the x direction. J extends 1 unit in the y direction. Labeling these, we have I and j. And using our right-hand rule, lying our hand perpendicular to the xy plane along the x-axis and curling in towards the y-axis, we get that I cross j is equal to k. To find j cross I, we still need to lie our hand perpendicular to the xy plane with our hand running along the j-axis, pointing in the positive y direction. Curling our fingers now in towards vector I, our thumb is pointing down, telling us that j cross I is equal to -k. Now that we know how to find the cross product, let's go back to example 4 from our second slide, where we were trying to find the equation of a plane given 3 points. In Monday's lecture, we found the normal equation of a plane containing a point and the normal vector, a times x minus x naught plus b times y minus y naught plus c times z minus z naught equal to 0. We're given 3 points. We can use those 3 points to find vectors that lie in the plane. Once we can find 2 vectors that lie in the plane, we know that the cross product of those 2 vectors has to be perpendicular to the plane in which the vectors lie. That's our strategy for solving this example. Let's start by finding our 2 vectors. AC is equal to head minus tail, 6 minus 3, -4 minus a -2, 5 minus 6. Which is equal to 3, -2, -1. When we're taking the cross product between 2 vectors, those vectors need to lie tail to tail. In our first vector, the tail is A, so in our second vector, we need to find AB. That is equal to 4 minus 3, -2 minus a -2, 9 minus 6. Equal to, that simplifies to 1, 0, 3. Are these the only two vectors you could use? No, you could use any combination of vectors as long as those vectors had the same tail. That means that your equation of a plane might not look like someone else's equation of the plane, but they're still the same equation of the plane. The normal vector to the plane is equal to the vector AC cross the vector AB, which is equal to, these are the same vectors that we used in the previous example. So we know this cross product is equal to negative 6i minus 10j plus 2k. Now that we have our normal vector, the negative 6, negative 10, and 2, we'll sub in for a, b, and c in the equation of our plane. And for the point x naught, y naught, z naught, we can use any of the three given points. It doesn't matter. One equation for the plane is negative 6 times x minus 3 minus 10 times y minus a negative 2 gives us a plus 2, plus 2 times z minus 6. And that is equal to 0. Finding the cross product involves a lot of algebra. And the running joke is that mathematicians can't add. So is there some way that we can check our work? We know that the vector u is orthogonal to v if and only if the dot product between the two vectors, u dot v, is equal to 0. We also know that the normal vector has to be orthogonal to both the vector ab and ac. So let's check our work and see if when we take the dot product of the normal vector with AB and then also with AC, do we get back 0? The dot product of n and AB is equal to, n is negative 6, negative 10, 2. AB is 1, 0, 3, which is equal to negative 6 plus 0, plus positive 6, which is 0. The dot product between the normal vector n and the vector AC is negative 6, negative 10, 2, dot 3, negative 2, negative 1, which is equal to negative 6 times 3 is a negative 18. Negative 10 times a negative 2 is a positive 20. 2 times negative 1 gives us a negative 2, which also simplifies to 0. So we know that our cross product is correct. You should check this every time. It's so simple, you can do the math in your head, but it will tell you right away if you've made some small algebra error when you're finding the cross product. This is a very handy property for us to have. What other properties does the cross product have? Given the vectors u, v, and w, and some scalar k, we've already discovered our first property. V cross w is equal to negative w cross v. We call this anti-commutative. Geometrically, this means that the vector v cross w is going to point in the opposite direction of the vector w cross v. The cross product obeys the associative property. kv cross w is equal to k times v cross w, which is equal to v cross kw. The next two properties are the distributive property. U cross v plus w is equal to u cross v plus u cross w. And u plus v cross w is equal to u cross w plus v cross w. Unlike multiplication, order matters here because v cross w is not equal to w cross v. The dot product between u and the vector v cross w is equal to the dot product of v with w cross u, which is equal to the dot product of w with u cross v. Right about now, you should be growing concerned because u cross w is a vector and v is a vector, and you can't multiply vectors together. Instead of the cross product, we should have the dot product. And now the property makes sense because u dot w returns a scalar, and we can multiply a scalar times a vector. This property is written correctly on your page, but I just wanted to point out how knowing the properties of vectors will help you to catch these kinds of small mistakes. We've talked a lot about the algebraic properties of the cross product, how to find it algebraically, and applications such as finding the equation of a plane if we're given 3 points, or to find the line of intersection between 2 planes. Let's take a look at the geometric properties of the cross product. Given these 2 vectors, a and b, does a cross b come out of the screen or does it go into the screen? If you lay your hand perpendicular to the same plane as your paper along the vector a and curl your fingers in towards the vector b, then we know that a cross b will come out towards you by the right-hand rule. The cross product is also helpful in finding areas and volumes of some of our geometric shapes. Let's sketch a parallelogram that's spanned by the vectors a and b. To do this, I'm going to copy our vector a and move it so that its tail lines up with the head of b. And now I'm going to copy our vector b to close our parallelogram. In general, the area of a parallelogram is its base times height. In terms of our vectors, we know that the base is the magnitude of a. But what is our height? To find our height, let's start by letting theta equal the angle between vectors a and b. We're looking for our height, which I've drawn in red here. And we know that sine of theta is equal to opposite over the hypotenuse, which in our case is h over the length of the vector b. Solving for h, we have that h is equal to the magnitude of the vector b times sine theta. Subbing that into our formula below, we have that the area of a parallelogram is equal to the length of the vector a times the length of our vector b times sine theta. From slide 3, when we first introduced cross products, we know that the magnitude of a times the magnitude of b times sine theta is equal to the magnitude of a cross b. So to sum it all up, that means that the area of a parallelogram spanned by vectors a and b is equal to the length of the cross product, the vector formed by a cross b. While it's true that the length of a cross b is equal to the length of a times the length of b times sine theta, and you could use this to solve for theta to find the angle between the vectors a and b, finding the cross product is a lot of work. You should never use that to find angles. Use the dot product instead. We know from our last lecture that cosine theta is equal to the dot product between the vectors u and v over the magnitude of u times the magnitude of v. Dot products are way easier to find, and there's a lot less room for an algebra mistake. So whenever you're looking for an angle between the vectors, make sure that you're using the formula with the cosine theta rather than the one with the sine theta. Let's do another example similar to this one. I've gone ahead and worked this one out for you, but I wanted to show you that just like we can use the cross product to find the area of a parallelogram, we can also use it to find the area of a triangle. Since the area of the triangle formed by PQR is half the area of the parallelogram formed from the vectors PQ and the vectors PR. We're given P is 1, 3, Q is 2, 1, and R is 5, 4. But that's in 2 dimensions, and we'd said the cross product only works in 3 dimensions. This is okay though, because our third dimension, Z, is just equal to 0. So we can change this, finding our vector PQ and using 0 for our Z component. Same with our vector PR, having 0 for our Z component and finding our X and Y components by the difference between the head and the tail of the vector. Finding the cross product between PQ and PR gives us the vector 0, 0, 9. The magnitude of this vector is the square root of 0 squared plus 0 squared plus 9 squared, which is just 9. 1/2 times 9 gives us 9/2. So the area of this triangle formed by the points PQR is 9/2. Thinking about this geometrically though, what does that mean if U cross V is equal to 0? And by the way, did you catch the mistake in the question above yet? The cross product between 2 vectors, in this case U and V, returns another vector. So even if U cross V is equal to 0, it's equal to the vector 0, not the scalar 0. U cross V is going to be equal to the 0 vector if and only if the length of U cross V is equal to the length or the magnitude of the 0 vector. This is going to be true if and only if the length of U times the length of V times sine theta is equal to 0. Since we know that the magnitude of U cross V is equal to the magnitude of U times the magnitude of V times sine theta, just subbing that in its place, and the magnitude of the 0 vector will be the scalar 0. The magnitude of U, this is a scalar, we have a number. V, that's a scalar, and sine theta is also some number. So the only way that the product of these 3 things is equal to 0 is if one of these things themselves are equal to 0. This is true if and only if the magnitude of U is equal to 0, the magnitude of V is equal to 0, or sine theta is equal to 0. Solving sine theta equal to 0, that means that theta has to either be equal to 0 or to pi. Theta is only going to be equal to 0 or pi if the vector U is parallel to the vector V. In other words, the vector U is parallel to the vector V if and only if U cross V is equal to the 0 vector. This is an interesting consequence of the cross product. It should not be used to determine if 2 vectors are parallel. If you want to show that U and V are parallel, we know that 2 vectors are parallel if and only if one vector is a scalar multiple of the other vector. If we can use vectors to find the area of a parallelogram, can we scale that up to volume? The volume spanned by three vectors, u, v, and w, is called a parallelepiped, and its volume is the magnitude of the dot product between u and v cross w. We won't do much with that in this course, but you will see it later on, and it has many applications. We can use it to determine if 4 points, A, B, C, and D, in R3 are coplanar. The points are coplanar if and only if the volume of the parallelepiped spanned by the three vectors is 0. We can also use it to find the distance from a point to a plane, which we've already done 2 different ways in our last lecture. It motivates the definition of the determinant in linear algebra. And once you get into multivariable calculus, it's the volume expansion factor when changing variables in triple integrals. I mentioned back at the beginning of lecture that there was an alternate method for working out example 3 to finding the line of intersection between 2 planes. In this last example, which I've already worked out for you, I left on the left-hand side of the page all the work that we did to find the line of intersection by parameterizing the planes, and our alternate method uses the cross product. Let's let L be the line of intersection between the planes. Then the cross product of the normal vectors of the 2 planes has to be parallel to L. To find the equation of L, we need 2 things. We need a direction vector and we need a point on the line. The cross product between the 2 normal vectors gives us the direction vector. Since this line extends infinitely, then there has to be some point on L where z is equal to 0. We just need to find the x and y values where that occurs. And since L lies on both planes, we can sub in 0 for both of the z components and eliminate one of our variables. Eliminating x here and solving for y, we get that y is -3. Subbing -3 back into either of the equations for our plane, we get back that x is 16, giving us the point in vector form 16, -3, 0. Using that to find the equation of our line, we have that L is equal to P, 16, -3, 0, plus the direction vector, 14, -4, -2, times t. Now you know 2 ways to find the line of intersection between 2 planes. So far, we've explored lines and planes and the interaction between the 2. In our next lecture, we'll introduce the vector functions of curves and also the applications of vector functions.